Okay, now we're going to put a little bit of math behind our induced drag so we can estimate it. We're not going to really derive this in full. If you take the aerodynamics class, we do go through a full derivation, but we're going to at least talk about some motivation here and get into the formulas and how we would do this. Okay, so let's jump in. Let me share my screen again. Okay, there we are. So the first concept we're going to talk about is called circulation. Circulation has this symbol gamma, and it is a path integral of velocity dotted into some path. The path is arbitrary, right? So we can take any path. The circulation is what's contained within this path. So for example, here's an airfoil. Here I've drawn the direction of circulation. And if you want to, you could think of it this way. Imagine that we had a free stream. So all the velocity was just coming over this airfoil straight. And we put in this circulation, think of it maybe like a little tornado, and we adjust it just the right amount that it's now going around this airfoil. So on the top, velocity is going to the right, same with the velocity going this way. So it actually speeds up over the top. And on the bottom, this circulation is going from right to left, which is opposite my free stream, so it slows down in the back. So I can adjust this properly so that I can get the right sort of velocities around this airfoil, okay? Just conceptually, right? We can actually kind of simulate this. We need a little more detail than that, but that's kind of the basic idea. And this spinning of the fluid, if you will, is related to the generation of lift. Formally, mathematically, we can calculate it by taking some contour around this airfoil here and doing this path integral. So if we took the velocity field, right, we went around this airfoil and just took the velocity in the direction of the path and did that integral, it would give us the circulation. And it actually wouldn't matter what that path looked like, if it was this shape or this shape. If it enclosed that airfoil, we'd get the same answer every time. Okay, I'm not going to prove that, but that's the case. So if we have the circulation, and I'm going to draw it on this airfoil again, it's generating some circulation, and I'm flying with some free stream speed v infinity. This formula here is called the cous theorem. The cous theorem tells me the direction and magnitude of the lift, or the force that I'm going to generate. So in this case, you can see by a cross product that the lift is given by the cross product of v and gamma. Gamma is given by the right-hand rule, so I curl my hand around gamma. It's like this, and my thumb points in the direction. So that's into the page. So gamma is pointing into the page. So v cross gamma, I again use the right-hand rule. V is going this way, left to right. I put turn my hand in the direction of gamma, right, which is into the page, and then my thumb points in the direction of the resultant force, which is going to be up. Okay, so this is my lift force. And remember that we said by definition that lift is perpendicular to v infinity. This is another way to say that in a formula sense, right? Because of the cross product, it will always be perpendicular to v infinity. All right, so the problem is though, remember last time we talked about this downwash. The airplane is flying straight with v infinity. So from the perspective of the airplane, the wind is coming in straight at v infinity. But because I'm generating lift now, I'm actually pushing air behind me, starting at the plane of the plane. In the geometric plane of the aircraft, I'm already starting to push air downward. So there's actually this downward component of velocity, and W is just the symbol we give for downwash. So that means the airplane is actually experiencing a velocity vector that looks like this, from the motion of the airplane, but also that downwash. So if we again look at that cross product, that means that the force vector is actually going to be perpendicular to that relative velocity, which means it gets tilted back. Okay, so the force is actually in this direction, which means it has a component upward. We reduce the lift a little bit, but we also have a component going backwards. And this is another way to think about induced drag. It's a little more abstract, but it's another way to think of it. The force in the direction of v infinity, by definition, is drag. So we can see that because there's downwash and we've tilted that force, we now have created a component of the force in our free stream direction, and thus drag. Like I said, this is a little more abstract. Doing it this way makes it easier to derive the formula, so I'm showing you this. But more fundamentally, I would think about what we talked about last time, where we have to leave energy behind because we're pushing air down. Thus, we must always have drag to have lift. It's actually not too hard to derive it from here, but I'm going to jump to the formulas. Oops, I skipped forward. I guess I kind of drew these. Here it is. Here's the formula we'll look at. From that, we can derive a formula for the induced drag. So this is what d sub I is. It's the induced drag. L is the lift. Q is the dynamic pressure we've already seen. B is the wingspan, which we've already seen. And now there's this new term, which is called the inviscid span efficiency. Okay. We'll leave it aside for the moment. Let's just assume it's 1 for right now. But everything else we've seen. Why do we call it induced drag? Well, the short answer is that the equations that govern this velocity field, we talked about these vortices, right, and their inducing velocity. Turns out it's exactly the same equations as the Biot-Savart law from physics. If you don't remember that, that's the physics that describes the magnetic field induced by an electric current in a wire. You got electric current, right? It induces this magnetic field. And I just said induces, right? And it's the exact same equations. So we say these vortices induce a velocity, and because it's that induced velocity that creates the drag, we call it an induced drag. Now let's go back and look at this formula and see if we can unpack this a little bit. What do we see, and we're just looking at the top one for now, what do we see are the major drivers for induced drag, okay? Well, there's a factor of pi, magical number that appears in a lot of places. Lift, right? Or in other words, the weight of our airplane plays a big role. If we make the airplane heavier by a bit, we're going to pay for it by quite a bit in terms of drag. This is one reason why, or really the main reason, as aircraft designers, we obsess quite a bit about drag. Although as we'll see with rockets, you gotta obsess about it even more. Because here with weight, we pay a big penalty in terms of drag. It's squared. We also see though that there's something we can do about it with another square term in the denominator. If we increase our wingspan, we can reduce our induced drag by quite a bit. We'll talk about this again in a minute, but you've probably observed this kind of thing in nature, looking at birds, seeing the differences in birds and maybe how some are more efficient than others. This wingspan is a big difference, right? Bigger wingspan means we're going to have less induced drag. Not necessarily less total drag, but less induced drag at least. Okay, Q. What is Q again? Well, let's remember what Q is. Q is dynamic pressure, 1/2 rho v squared. So what does that mean? Well, density, we don't, generally have tons of control over that, but the speed we do, and we can see that if we fly slower, our induced drag is actually worse, right? Flying faster reduces our induced drag. So if we go back to this plot, speed, drag, what it looks like is that parasitic drag actually does look like this. This is the kind of plot that many of you drew. Parasitic drag, it is C or dP. It's going to be like a drag coefficient times 1/2 rho v squared times an area. And you can see there's that v squared term, so it varies quadratically. However, induced drag, boy, not drawing that super well. It's going to look something more like this. Oh, come on, it doesn't go through. Yeah, even better. I'll just get rid of the axes and then I can draw it later, I guess. Okay, induced drag. And we can see that induced drag is going to be L squared over 1/2 rho v squared times some other constants. I'm just not going to write it. So you can see there's that 1 over v squared relationship. As v gets bigger, my induced drag gets smaller, but as v squared goes to 0, my induced drag really skyrockets. So my total drag, right, is going to be, I don't know, something like this. Okay, here's total. notice that the minimum is actually going to be right where these cross, where the induced drag and the parasitic drag cross. So that's why the curve looked the way that it does. At high speeds, we're going to be dominated by the parasitic drag. At low speeds, the induced drag. We're not generating lift very efficiently because we're just flying really slow. And so that's just going to cause us. Another way to say this, if I'm flying really slow, okay, there's not a lot of air that I'm moving through for a given unit time. So to generate the lift I need, the momentum I need to push the air down really fast, okay, to generate the same force. Whereas if I'm flying really fast, I've got a lot of mass, a lot of air that the mass flow rate is really high. So I'm moving through a lot of air really quick. So I actually only need to put a little velocity on that air. So I can get the same force by taking a lot of air and moving it a little bit, or a little bit of air and moving it really fast. And it's much more efficient to take a big chunk of air as I go through really fast and push it down a little bit to generate that force. That's why the induced drag is much less at higher speeds, okay? So we talked about 3 things we can do as an aircraft designer to reduce our induced drag. Get the airplane lighter, increase our wingspan, fly faster, although that's not necessarily great for total drag. There's really sort of an optimum there. The last one, which is and talked about, is this term here, E-inviscid. This is governed by the shape of our lift distribution. So we're going to talk about that in a second, so just hold on to that. The other thing I have here, this is the same equation, we've just normalized it, right? We use the same definition of a drag coefficient. It's the drag coefficient divided by dynamic pressure in a reference area. And remember again that aspect ratio is span squared over reference area. So this is the same equation, just in a non-dimensional form, which, depending on what you're doing, either useful, though if you're thinking about what to do to reduce drag, it's helpful to think about actual drag, because sometimes you can reduce your induced drag coefficient while still actually increasing the induced drag. Okay, so actually let's look at some pictures here. I mentioned birds. These are like 2 good contrasts, right? A soaring bird like an eagle, large wingspan, efficient, right? It can fly for a long time without doing much. Doesn't have to flap because it's got that long wingspan, low induced drag, very efficient. On the other extreme, a hummingbird, very small wingspan, has to expend a lot of energy, but these are also, there's, like in all things in engineering and aircraft design, there's always these trade-offs, right? Long wingspan, we get high efficiency, but we get kind of slower maneuverability, whereas although these eagles, you know, they can also kind of contract and do a little bit of both. Hummingbirds, very small wingspan, but very, very maneuverable, right? They can change direction really quick. They, of course, see this reflected in aircraft designs too. Large wingspan on the right, very efficient, can glide very far, or can be, with powered flight, get very far range, but not very maneuverable, right? They can't pull in their wings, so they're gonna take longer times to turn, and so there's again pros of stability, but not very maneuverable. Whereas a fighter, very short wingspan, but very quick, able to maneuver and change. So depending on your requirements, one or more are, you know, you have to make some trade-offs. Again, you're going to pay for that in terms of induced drag. Okay, so I mentioned the shape of the lift distribution affects that last term. So what does that mean? Let's say here's a back view of the airplane. So here's a wing, and let's just say I put a fuselage in here. Okay, so I'm looking at just a back view, wing, fuselage. The lift is going to go to 0 at the tips. There can't be some finite pressure outside of the tips, right? Because there's a continuous fluid. So it must go to 0 at the tips. The pressure is going to have to equalize at some point. The ideal lift distribution, actually this is not necessarily always ideal, but simplistically the ideal in this context is an elliptic lift distribution. Elliptic means the shape of that distribution is an ellipse. If I put the equation in an ellipse, that's what it looks like, okay? So I generate a lot more lift on the inboard, and with the shape of an ellipse, I taper that lift towards the outside of my wings, and I go to 0 at my wingtips. An elliptic lift distribution gives me an E-inviscid of 1. And for a planar wing, which means it's on a plane, there's nothing sticking up like winglets or things like that, it's just on a flat plane. For a planar wing, that is the best I can do. So for a fixed span, this gives me the minimum induced drag. If I had different shapes of lift distribution, so I could change this any way I want by twisting the wing. Here's a different one. Or I could put, maybe more lift towards the center. I have other shapes. I could have, all sorts of things. I could have weird ones where I've got lift on the outside and this would be really bad, less on the inside. All right, these are all going to have an E inviscid less than 1. In fact, that one is going to be much less than 1. If we go back to our formula here, anytime E inviscid is less than 1, my induced drag is going to be higher. So the best I can do for a planar wing is to get an elliptic lift distribution. And most airplanes are going to have something quite close to an elliptic distribution. They'll be designed that way. We actually usually design it so that the lift is slightly inboard, right? Not perfectly elliptic. We actually move a little bit inboard relative to outboard, and that's just because of the structure. By pulling a little bit inboard, we don't sacrifice much in terms of span efficiency, but we also reduce our bending moments because we have less loads further away. So that's just a trade-off in dynamics and the structures. So we can actually even do better than E inviscid of 1, but that means we need to be non-planar. Like if we had winglets, you can get a little bit higher. We're of course also adding parasitic drag though, because now there's more wetted area, so it's always not necessarily an obvious win. We've also added maybe more weight because now we've got bigger bending moments. So again, a trade-offs there, but in general, many airplanes, not all, but many airplanes will have close to an elliptic lift distribution because of this property. All right. One more thing we need to talk about to put together. Remember that we said that this is all inviscid. This behavior is completely inviscid, right? If there was no viscosity, we still, to generate lift, have to have the air push us up. So we got to push the air down, leave momentum behind, leave energy behind. That's drag, right? We left energy behind. Well, because we generated lift, though, we actually do increase the parasitic drag somewhat too, but we usually keep track of that as part of our induced drag. We call this the viscous component of induced drag. So what we talked about before was the inviscid component. There's now a viscous component. There's the interaction between my lift and viscosity, and it generally is going to follow this kind of form that it's going to be proportional to my lift squared, and it's going to vary with my parasitic drag. So as I have more parasitic drag, I'm going to have more viscous dependent lift drag. And this K, we're just assuming it's a constant, right? There's some proportionality. And this is a pretty reasonable approximation for many airplanes. The K, though, may vary. If you want a number, here's a sort of typical number. That's really more for transport size aircraft, but it will be okay enough for the things we're doing. Again, this is kind of rough conceptual design things, but here's the thing that we're going to do though. We want to put these together. We don't usually use this formula directly. We're going to put it together with the things that we already know. So here's what we already got. We had before that the induced drag coefficient looked like this. CL squared over Q pi, no, I'm writing the other one, Q aspect ratio, no, sorry, pi aspect ratio. I'm writing the full drag. The drag coefficient is pi aspect ratio E inviscid, okay, like that. That is the inviscid component. And now I need to add the viscous component to get the total drag. Okay, so again, inviscid, viscous part, and the total is my total induced drag. Okay, so I don't love that formula because it's kind of ugly. We had a nice formula before and now it's kind of a mess. So here's the thing that we do. We're going to factor out, notice how there's a CL squared in both. We're going to factor that out. Actually, we're going to factor out a pi aspect ratio, even though it doesn't appear in both. We're just going to factor out anyway. And now I've got just 1 over E inviscid on this side. And this term, we're going to have the K and CDP are left over, but because we added this pi aspect ratio on the bottom, we're going to have to multiply that here on the top. Okay. So I've done nothing special, just kind of just kept everything the same. What I'm going to do now because I liked this formula and I want my new formula to look similar, notice that it looks very similar except for the E part. We are just going to call this whole thing here, this whole term here, right, all of this. We're just going to define a new variable and call this 1 over E. Just make up a symbol E, right? So now my total induced drag looks exactly like it did before, except for instead of writing E implicit, it's E. This is the E total. We call this Oswald's efficiency factor. And the definition of it, well, I mean, this is kind of self-defining. But from this formula, you can just solve for E, right? It's the inverse of that thing in the parentheses. So what this does is it allows us to use the same formula we were using before, but all we have to do to change from the inviscid one to the viscous one is just use a different factor. So just to give you some idea of what these would typically look like, E inviscid is usually close to 1 because we try to design something close to an elliptic, so typically say about 0.98. Whereas the Oswald's efficiency, once we compute this, right, we add in the drag and actually compute this because these are all numbers that we're going to have. We showed it. We talked about computing this last time. This is just a constant. This we already have, and the aspect ratio is our geometry. So we can compute E. It's going to be somewhere around like say 0.8, maybe 0.7 to 0.85-ish. So it's definitely lower, which means the induced drag is higher, which makes sense, right? Because we just added a viscous component to it as well. Okay, that scared me. Get a text message. All right, so that is it for today. Next time we're going to talk about a third type of drag. So we've talked about parasitic drag and induced drag. We're next going to talk about compressibility drag. And those are the three things we're going to put together. Of course, fundamentally, there's not really 3 separate types of drags. This is the way we think about it conceptually, and it makes it easier from an equation standpoint to break it up. But at the end of the day, it's just a total force. It comes from pressure and shear stress. But it helps to think about the main driving mechanisms, the first being mainly viscosity, the second one being lift, and the third one, as we'll see, will be Mach number, high speed, the compressible nature of fluid. All right, see you next time.